As we are going through a new era of technology, the demand for a more flexible network increases. A flexible network that can resolve complexity and overcome distortion. Machine learning, particularly the subfield of artificial neural network, is the solution we look for. An artificial neural network is a model of information processing inspired by the way a human's nervous system works. It consists of a huge number of interconnected elements called neurons, all operating in harmony to solve a specific problem. An artificial neural network is constructed to process information using pattern recognition as a result of a process of training.
Because the neural network technology is the basis for automation. And I really believe that the next revolution will be automation. And neural networks, machine learning, data science is the basis for the next future, the next revolution in IT and ICT. So neural networks are going to stay forever.
Deep learning refers to the ability to represent the information by means of such neural networks that are very, very complex in the sense of embedding into these billions of neurons and hundreds of layers, and representing through this type of very complex neural networks any complex phenomenon, any complex situation that you want to mathematically model and capture.
Information are processed in the model of the digital communication system. The model is composed of an encoder where the information are transmitted, a channel that is the medium information passed through, and decoder where information are received. For channels can be noisy and distortive during transmission, some information might be corrupted and received in error, and that is why error-correcting codes are used. The idea of these codes is that the sender transmits the information with added redundancy in the form of an error-correcting code, which allows the receiver to detect a number of errors in the message and correct them without retransmission, which can be costly and impossible in some situations. The decoding process can be complicated and inefficient when correcting errors. For conventional error-correcting codes, the decoding is direct, but for complex codes resulting from highly distortive channels, decoding is almost impossible. For that reason, this project proposes the use of neural network decoders.
If you take any situation, any complex system, it can be seen like if you abstract it, you can write down a model for that system. Okay, and in order for dealing with information that is circulating within the system, you need a coding structure, whatever it is. Once you have this model, then of course it comes as a necessity the need for decoding information. So it's more general. The application can be transversal.
Implementing a neural network decoder will make a wider impact on future technology and will benefit in many applications such as telecommunications, cybersecurity, and smart cities.
It could improve the encryption and decryption of data because of the neural network was able to determine all these channel problems. So if even the encrypted data has been corrupted with the channel, okay, then the neural network will be able to know these kinds of bits, correct them, so they will be available for decryption.
The long-term goal is to apply artificial neural network technology to all components of the model of digital communication. Though we are applying this technology to the decoder side of this project, the success of this implementation will create a more robust communication system that is able to decode complex codes and overcome distortive mediums with higher flexibility. In this project, a decoder will be made out of coding software, and the signal is a binary code that will be enhanced to make the digital decoder robust against complex codes and more flexible.
Now, when you talk about the decoder or encoder architecture that can be used for neural network, that may take some kind of coding from one side and translate it to enhance a digital coding in another side, taking binary to digital, or using binary coding to improve the digital signals, is very important. Now, also if you look at it from the other side of telecommunication, you'll find that for this kind of technology as neural network can also be used on subscriber side. Learning will help, machine learning will help the telecom operators in subscriber profiling, for example, and analyzing offer conversation rate, content usage trends, and network activities. It also helps them to push some kind of offer that is tailored as per subscriber need in the right time. So all these kind of analytics that machine will do certainly will have a value for optimizing, whether it is in the customer side or it is the network side, and doing it faster, better, and quicker. So such a solution, when we say, well, it is going to be suitable for Qatar or for other side of the world, telecommunication network will be more or less same, whether it is in Qatar or in China. Actually, if this project or your project becomes so successful, you are going to add a value, whether it is for Qatar telecommunication market or some other markets, or maybe if there are futuristic kind of manufacturer in Qatar that develop all these kind of solution for telecommunication.
The main error correcting codes used for this project are the Hamming codes for which the system will be trained. Here we will consider the Hamming code 7 for example. The first step is to determine M, the number of check bits attached to the message. In this model, M is equal to 3, the primitive length N equals 7, and message length is equal to 4. The second step is constructing the Hamming matrix with dimensions M by N. The right side of the matrix refers to the parity bits, while the left side refers to the information bits. From the Hamming matrix, we can extract the parity check equations. In the third step, C is a vector space that represents the code words. K will represent the dimension of C, which will be equal to 4 in this model, or simply the number of information bits. From the dimension, we can compute the number of code words that is equal to 16. The fourth step will be writing the list of 16 code words from the parity check equations. The fifth step is computing the syndrome, which is the multiplication of the H matrix by the transpose of an input vector. Syndrome here will be 0, which means no erroneous bits are detected, because vector space C is what the H matrix is originally reconstructed from. In this example, we consider a random input vector V to compute the syndrome. After computation, we get syndrome equal to 1, which means an erroneous bit is detected. The sixth step is finding this erroneous bit. We define input vector V as a summation of vector C and vector E, that is the error vector. Syndrome will be equal to the expansion of multiplying matrix H by vector E. In the last step, this expansion is equated to 1, the result of syndrome vector with respect to the input vector V. And we find by comparison that the erroneous bit is bit number 3, and therefore the value of the bit is inverted. Now vector V is corrected and belongs to vector space C.